Hello! In today's session, we're going to dive into one of the most versatile and important building blocks in analog electronics, the operational amplifier, or op-amp. By the end of this video, you will be able to describe the key characteristics of an ideal op-amp and understand the basic structure of its internal circuitry. Op-amps are the core of many analog systems, from audio amplifiers and filters to precise measurement circuits. But what exactly is an op-amp? Fundamentally, it's a very high-gain differential amplifier. This means it takes the difference between two input voltages and multiplies it by a very large number. To understand its function, let's start with a simplified model, the ideal op-amp. We can represent an ideal op-amp with this symbol: two inputs, a non-inverting, one marked with a plus sign, and an inverting one marked with a minus sign, and one output. The ideal op-amp follows two golden rules that make it incredibly easy to work with in circuit analysis. The first rule is that no current flows into the input terminals. In reality, there is a tiny leakage current, but for an ideal op-amp, the input impedance is infinite. Think of it like a perfectly insulated wall. Nothing can get through. The second rule, which is the most powerful in circuit analysis, is that if the op-amp is in a closed-loop configuration with negative feedback, the voltage at the inverting input is forced to be equal to the voltage at the non-inverting input. This is often called the virtual short concept. It's a key simplification that allows us to quickly solve op-amp circuits. Now, of course, a real op-amp isn't ideal. It has limits on its output current, bandwidth, and slew rate. But for most applications, the ideal model is an excellent starting point. So, how is this magical device built on the inside? An op-amp is an integrated circuit containing anywhere from 6 to 20 or more transistors, depending on its complexity. Its structure is usually divided into three main stages. Let's look at a conceptual block diagram. The first stage is the differential input stage. This is where the op-amp calculates the difference between its two input voltages, V plus and V minus. This difference, amplified slightly, is then fed into the gain stage. This is where the op-amp achieves its enormous voltage amplification. Finally, we have the output stage. This stage doesn't provide more voltage gain, but it buffers the signal, allowing the op-amp to deliver a significant output current and drive external loads. So, we have a differential input stage for subtracting, a high-gain stage for amplifying, and an output stage for driving a load. Let's explore each of these stages in detail, starting with the differential input stage. The first and arguably most important part of an op-amp is its differential input stage. It's the diff-amp in differential amplifier. Its job is to amplify the difference between the two input voltages while rejecting any signal that is common to both. This is called common mode rejection. A basic differential pair consists of two matched transistors, here labeled Q1 and Q2, sharing a common emitter current source. The current source, I sub E, ensures a constant total current flows through the emitter junction, which is then split between the two transistors. Here's the clever part. If the two input voltages, V plus and V minus, are the same, then because the transistors are matched, the emitter current I sub E splits exactly in half. Half flows through Q1 and half through Q2. The voltage drop across their collector resistors will be identical, and their output voltages will be equal. There's no differential output. If V plus and V are equal, the collector currents are equal, and the output difference is zero. Now, let's say we apply a small differential signal. Let's make V plus a little bit higher than V minus. The slightly higher voltage at the base of Q1 causes more current to flow through Q1's emitter. Because the total current I sub E is constant, the current through Q2 must decrease. This unequal splitting of current leads to a voltage difference at the collectors, which is our amplified differential output. So, the differential stage successfully suppresses common mode signals and amplifies the difference. In a real op-amp, this stage is followed by more sophisticated gain stages to achieve the incredibly high overall gain. Following the differential input stage is the high gain stage. This is where the op-amp really earns its title, as this stage provides the vast majority of the op-amp's voltage gain. The output of the differential stage is typically fed into one or more intermediate gain stages. These are usually common emitter amplifiers, cascaded together to multiply their gains. For example, a common emitter stage looks like this. It takes the differential signal as its input and outputs an amplified, inverted version of it. An op-amp might have several of these stages in series. The gains multiply, resulting in a total open loop gain, A sub OL, that can be well over 100,000, or even a million. This gives us a monumental voltage gain. A tiny difference in input voltage can produce a very large output voltage. You might ask, why bother? A gain of a million is almost too much. The answer lies in negative feedback. When we apply negative feedback to such a high-gain amplifier, the closed-loop gain becomes predictable and stable. This is a topic for another video, but the high open-loop gain is what makes this closed-loop operation so effective. Finally, we come to the output stage. The high-gain stage generates the amplified voltage, but it often has a high output impedance and cannot deliver much current. If we tried to connect a loudspeaker to it, it wouldn't work. The output stage solves this problem. Its primary purpose is not voltage gain, but rather to act as a current buffer or power amplifier. It takes the high-voltage signal from the gain stage and allows the op-amp to drive a significant output current into an external load, like our loudspeaker. The most common configuration for the output stage is a push-pull amplifier, typically using a complementary pair of transistors, like an NPN and a PNP, connected in a Class B configuration. When the signal from the gain stage is positive, the NPN transistor, Q3, conducts, pulling current from the positive power supply and pushing it into the load. The PNP transistor, Q4, is off. When the signal is negative, the PNP transistor, Q4, conducts pulling current from the load and sinking it to the negative power supply. The NPN transistor is off. Together, these two transistors provide current amplification for both positive and negative halves of the signal, ensuring that the op-amp can deliver power to the load while maintaining a low output impedance. This creates a low resistance path for the output signal. Let's put it all together and see how these stages are interconnected in a complete op-amp, like the venerable 741. Here we see a simplified schematic, which is still quite complex. It shows how the different parts work in concert. The two inputs, invert and non-invert, feed into the differential input stage. The output of that stage drives the gain stage, which then feeds the push-pull output stage. Finally, the output, Vout, is connected to the output stage's common emitters. Now, you might have noticed a capacitor in the middle, typically labeled C1. This capacitor is crucial for frequency compensation. Without it, the op-amp's phase shift would reach 180 degrees, at a frequency where the gain is still greater than 1. When negative feedback is applied, this phase shift becomes positive feedback, and the op-amp oscillates wildly. The capacitor provides a dominant pole in the frequency response, causing the gain to roll off at a controlled rate, ensuring the op-amp remains stable with negative feedback. This makes it much easier and more predictable to use. So, we've taken a deep dive into the internal structure of an op-amp. Let's quickly recap what we've learned. We started with the ideal op-amp model, learning its key rules, infinite input impedance, and the virtual short concept. We then dissected the op-amp into its three core stages. The differential input stage subtracts the two input signals and provides common mode rejection. The high gain stage multiplies this difference by a huge factor. And the output stage provides current buffering to drive external loads. Finally, we saw how a compensation capacitor ensures stability. You now have a solid foundation for understanding how this incredibly powerful integrated circuit works on the inside. Knowing this internal structure will help you diagnose problems and predict behavior when working with op-amp circuits. Thank you for watching. I hope this explanation has been clear and helpful.